All right. Hello, everyone. Thank you for coming to our regular seminar. It's a pleasure to have here with us today Dr. Tong from Cornell University. He's from the ECE department or School of Electrical Engineering at Cornell. He got his degrees in 85, BS and MS in 85 from Beijing, Tsinghua University in Beijing, and his PhD from Notre Dame University in 1991. And he was a postdoctoral in the Information Systems Lab at Stanford. And following that, he went to Virginia University of Connecticut. And then he joined Cornell University in 2000. 98. Okay. And he was also a visiting faculty professor at the Delft University, a Corwith visiting professor. He's very well known in the whole area of statistical signal processing, and more recently in communications and sensor processing. And he's an associate editor of information theory, transactions, and he's been involved with the Signal Processing Society for many, many years. And it's a pleasure to have you here. He's currently the Irwin and Joan Jacobs Professor. I'm sure you know who Jacobs is at Cornell University. It's a pleasure to have you here, and thank you for coming.
Thank you, Hamid. Really a pleasure to have a chance to get out of the snow in New York, visit this beautiful campus. So I will talk about some of the things I actually got involved accidentally a few years back. In fact, the people here actually have worked on similar kind of problems. I'm trying to cast this as a detection and estimation problem, but it has implications in various fields. So I will talk about distributed flow detection via timing analysis. Okay, so I'll just start with something rather generic. So you have many nodes. They're transmitting. The question we want to entertain is a particular node talk to another node through intermediate steps? Okay. Are they talking to each other? Are they communicating? You can imagine these can be generalized to scenarios like this group of people doing some kind of chatting. Is there a multicasting scenario, someone streaming videos to a group of people? So this is the basic question. And if you can measure the transmission activities, and say nobody else is transmitting, you monitor these three nodes, and perhaps you will be able to find there's some transmission patterns of their activities, and you can say, looks like they are talking to each other. Okay, so if you can measure it quietly. And of course, maybe they're not. They are just talking to their individual neighbors. Then perhaps you will get transmissions that are look statistically independent. There's no fixed pattern. There's no response. So which scenario? I guess one can formulate this as a hypothesis testing problem. But usually things are much more complicated because these nodes, even if they talk to each other, that's not just what they do. They may route packets from other users. They may talk to you for 1 second and another second talk to another person. And you will get things that are patterns of transmission that correspond to some kind of behavior get embedded in many other transmissions. So for those of us working on signal processing, you can view this as looks like it's a signal in noise, except what we have are only timing. Okay. So I guess the point I'm trying to make is that the timing traffic information is relatively easy to obtain in wireless networks. In fact, you could just build a simple energy detector. You don't need to do anything. You just monitor, tune to a particular channel. You can record when this person is transmitting. Another point is that if you get these records of nodes transmitting, it will reveal certain networking information. Is this particular route being used? Are there two-way communication between two nodes? Okay. So on one hand, it's rather easy to obtain this information. On the other hand, this information does tell you something about a network operation. In contact with cryptography, that only protect the content of the communication, but it does not protect the act of communication. Okay. So the underlying question we are interested in is, to what extent timing information reveal the network operation? You can say, why do you care about something like this? Well, maybe you want to learn the behavior of people, how people use network. If you're vicious, maybe you can figure out the particular route is more important, and you can jam it at a time that most critical. So clearly there are implications in securities and even privacies of communicating, right? So you may not want to know, you may not want your advisor to know your access in certain websites. And so you want to protect the timing. There are other related problems when I give talks and people will say, oh, this seems to be related to this. I'll mention two. One could be you have sensors deployed in a sort of crowded area, and you do something rather primitive, not things like taking pictures, but maybe you just record the footsteps, the timing of the footsteps. Right? So from that, can you figure out, for example, there are certain patterns of how a group of people move? This is another case, and the people working on neuroscience, they record neural spikes. Okay, so there actually is a pure timing, extracted a pure timing sequence. And would you be able to figure out, for example, a sequence of neural reactions from these timing patterns? Right? Individually, they look rather innocent, but there clearly seems to be some kind of pattern embedded in such measurements. Okay. So my problem is that given this kind of timing measurements, can you detect there's underlying flow of events or flow of information? So I'm going to focus primarily just on the detection of a sequence of packet transmissions in a network. Okay, so this is what I want to talk about, and I'll talk about the formulation of this, and I'll give a precise definition of what I mean by information flow. And I will then formulate this as a hypothesis testing problem. I will describe some basic limits that what can you detect, what you cannot detect, and some algorithms, and then I will look at the distributed case in which you can imagine these traffic sensors are distributed in a network, and somehow these measurements have to be transmitted to a place so that processing can be done. And you can imagine this is an enormous amount of record, and transmission has to subject to some kind of rate constraints. How do you deal with issues like quantization, and what information are most relevant for you to deliver to a central processing center? Okay, so I'll show some numerical and experimental results. Okay, let me just describe the model of this. So we'll consider a set of nodes they are transmitting. And I'm going to assume there are some traffic sensors. So these are eavesdroppers. And they will tune to a particular node. I'm going to assume that each node will transmit with its own transmission code. It's called a transmitter-directed transmission. So this node can tune to that particular frequency band. It will record a sequence of transmissions in time. Okay. It cannot distinguish whether it goes there or there. It can only record, okay, this is the time this guy is transmitting something. So I'm not allowing you to open up the packet, look at the source destination. You can only say, okay, it's transmitted at this time. Okay. So they are monitored a set of nodes. So that's why we're assuming that all the transmissions are encrypted, so there's nothing you can gain by looking at them. Packets are just points. They're just point on a real line. So we're dealing with point processes without identity. Okay. Any additional information, of course, you can exploit to make this problem a little bit simpler, but we'll try to abstract the problem to the point that, okay, not much you can gain from looking at a specific packet. So what do we assume about the eavesdroppers? So they can measure the timing epochs. We're going to, for the most part, assume this measurement is accurate. Okay, and you have a perfect sensor fusion in the sense that they will transmit their measurements like this, perhaps quantized in some way, to a fusion center in which all the measurements are collected and then processing is done. Okay, so we're not allowed the eavesdropper somehow take the measurements and manipulate it. So these are honest eavesdroppers, not someone who is sort of try to fake data. Okay, so that's what I mean by sensor fusion is perfect. Clear so far? Okay. So I have to define what the things I want to detect. I mean by information flow. So I'm going to monitor a sequence of nodes, R1 to Rn. And I will say that this sequence of nodes are transmitting or carrying an information flow if each packet in one node will be mapped to the subsequent nodes. And this map has to be causal. That means this packet cannot map backwards. And it has to be one-on-one mapping. So that means all the information flow, the packets are preserved. Okay. So it's a causal match. Okay. So if these two nodes are form a link, and then every packet here will be forwarded there. Although I'm not specific about when it's forwarded, but it has forwarded after it arrived in the first node. So causal match is what I mean by information flow.
So you're not allowing for losses?
For information part, I don't. Okay. So, but I'm not going to add noise to it. So I'm going to consider two hypotheses. Hypothesis 0, all the transmissions are independent. You're just talking to your neighbors. You're not trying to forward any packets. So you just have independent transmission. Hypothesis 1, your transmissions are made of two parts. A subset of transmissions form an information flow. In this case, this packet flow from node 1 to node 4. This one goes there. But some of these other things are just things you multiplex, and you may transmit dummies. You may hear something someone else is transmitting. So when you measure the transmission activity, a subset of these transmissions would correspond to one particular information flow. So that means these packets has to be this one. So this has to satisfy the causal match condition. There is a causal match. Okay, you see that here. I'm allowing you to sort of swap ordering. I don't really care because the only thing you see are points. You don't have any identity. So that's hypothesis 1. You can view this as a signal plus noise. The signal part form these kind of flow conditions, has to be satisfied. The noise part is independent. Actually, I don't really care about how noise, once you will see, I will go on. I don't really care about the noise statistics.
But you seem to violate the one-to-one mapping, though, from the green one to...
Yeah, so this, a subset of transmissions that they have one-one mapping. Which one this?
From S3 to S4.
Uh-huh.
You seem to have a 1-to-2 mapping there. Is that true or not?
No, I'm sorry, this is not meant to be a connection.
Oh, okay. All right. Okay.
Artifacts of my drawing.
Yeah. Okay.
Yeah. This is, just illustrate, this is the delay.
Oh, okay.
Okay. So, but I need to put some constraints on to make this problem possible. You can imagine that I'm going to record, the transmission for a year, and after 3 years, I, spill them out, and you are hopeless to detect such a thing. So I'm going to put constraints on flow in the following way. If you are forwarding a packet that is part of information flow, you have to do that within a deadline, delta. This means that if this is information flow packet, I have to transmit forward to the next one within certain bounded delay. Okay. The rest of them I don't really care. Okay. So there's a strict bounded delay constraints, or you can formulate this as average bounded delay constraints. So on the average, if it's part of information flow, you will forward that within 1 second or 1 millisecond. These two actually are quite different problems. This is much more difficult to do. I'm just going to only consider this. Another constraint one can consider is called so-called memory constraints. So which means that each node, I don't have a strict delay constraints, but I can only store these many packets locally. So if I forward, I cannot store a lot. Okay. So there's a memory constraint that one can study. Yeah.
So when you have the delay constraint, is this for packet or is it for flow? Because you are detecting the information.
Yeah,
flow.
Each packet. Okay, this constraint is each packet. If it's a part of flow, it has to be forward within delta.
Okay.
Every point. Every packet that belongs to this flow has to be forwarded within delta. But other than that, I don't have anything.
So you don't have the delay constraint. Like say, if there is a flow, we have the starting point of a flow, and we have the ending point of a flow. You are not looking at the delay. The delay constraint for the entire flow, but for the packets.
Yeah, the entire flow, if you define it by when it starts, when it ends, it will also satisfy delta because the first packet has to be forwarded within delta, the last one has to be forwarded within delta. So the whole thing will end by delta.
Yeah, the only difference is if we look at the delay constraint for the networking flow, then we have to think about the network conditions. For example, the bandwidth, whatever, kind of the transmission delay. But if we look at a specific packet delay, then we are not looking at kind of the...
Yeah, so yeah, I don't know how to answer that. I guess by definition you are saying that I guess the network flow delay, you mean when it starts, when it ends, the first and the last one, right?
Right.
But clearly the last packet has to, so you don't put any constraint in between. So you allow things like, okay, some node are really put a lot of delay, other put less. Yeah, that I think would make the problem more difficult to solve.
Okay.
Definitely. You will see why it's difficult, that problem. At least my algorithm won't work. Even for this one, it's rather difficult, average delay. Because some node can forward things quicker that provide opportunities for other nodes sort of store up data. And then once you allow them to have a very long delay, it's very difficult to detect. Okay, otherwise clear? Yeah.
So we just monitor one flow, or we monitor multiple flows.
Yeah. So clearly recognize that these are not two complementary hypotheses, right? So if this is not true, doesn't mean that it has to be this, right? It can be okay. Something comes in here, exit there. That's what you say partial flow. I'm not considering that. Okay, I'm considering. For example, you can sort of develop some kind of strategy. I'm looking at 2 at a time and 3 at a time and see to sort out whether there is flow. But right now, I'm not considering that. So your question is, do you consider some kind of partial flow or multiple flows? There's another thing that goes on here. Is that what you mean?
So S1 to S4 are four sensors or
four nodes
for each job.
4 nodes I'm monitoring.
Oh, okay. Okay.
So I'm putting a sensor on you and I'll monitor these. I'm just trying to see whether there's something goes to you.
Among these 4
Yeah.
nodes. Okay.
Another thing that's sort of a point to mention is there is a direction. Okay, so we're working on things like a bidirection. Then you have a lot more hypotheses to do.
So you must be working off of some master clock, you're assuming, right?
Yeah. So each one has its own timing. Okay, so you will see that the precision of timing will not be critical when it depends on what delta is. Okay, so if the delta is very tight, then your precision has to be tight too. So right now, let's just say perfectly synchronized clock. Good? Okay. All right, so now I'm going to address the problem of rates. So each one of these measure these timings. Hypothesis 0, hypothesis 1. I want to introduce one terminology, that's chaff, which in the context of signal processing will be noise. So these are packets that's a part of flows. Everything else, I call them chaff packets, or in signal processing will be noise. Okay. These will be the W's. So they take measurements, and you're going to have to record, you're going to transmit these measurements to a fusion center, which is constrained by some rates. You have certain bits per second for you to do. So which means that you need to quantize, because all these measurements are real numbers. You need to quantize them. So these are a rate R1 for between sensor 1 and the fusion center, and fusion center 2 will be R2. Okay. So this represents the code words you will send to the fusion center. And the fusion center would get these measurements that's quantized, will make a decision whether this is true or that is true. Right. So the whole problem can then be formulated as one of designing these quantizers. How do you quantize these timing measurements? And designing the fusion center decision rule detector so that I can distinguish these two hypotheses reliably. By reliable, I mean in particular as you collect more and more samples, the error probability should go to 0. Okay, reliable, I mean that. Any finite n, you would have error probability, but in this case, you want error probability to go to 0. Okay, so sounds like a classical problem, at least in the context of detection. Once you set up the hypothesis, you are essentially detecting independent transmissions against something that's not independent. Okay. Independent being these nodes transmitted independently, not you have something that goes to them, right? So there are roughly two broad classes of distributed detection approaches. One is what I call distributed detection without coding, pioneered by Tanyan Sandel in the early 80s, and Tsitsiklis has done a great deal of work. And here you're talking about essentially a single measurement. Each one take a single measurement, can be a vector. You transmit it to the fusion center, and the fusion center will make a decision. Okay. Now, the point here is usually this kind of problem would assume that given a particular hypothesis, the measurements are statistically independent. The so-called conditional IID assumption. Usually you'll have some parametric model for each hypothesis. Here, as you can see, that I'm not really dealing with parametric model at all. And it is clear, although under H0, the measurements here will be independent. Under H1, it cannot be independent. It has to, because this is forwarding some of the subsequence. Another approach is the so-called CEO approach, in which you are allowed to consider not just single measurement, but the sequence of measurements. Okay. Originally framed by Berger, and there are lots of work along this line. So this allows you to code your transmission across time, and typically they remove the condition that the measurement and different sensors are statistically independent. They can take care of cases that measurements are statistically correlated, but they usually would assume that in time, in fact, all the results assume that in time they are independent. So you view this as drawing samples from joint distribution, and you draw them repeatedly. Okay. You can see that here we are dealing with timing, and the conditional IID is clearly not satisfied. But let me give you an example that shows why this is an extremely bad model to use. Aswady and Chizar considered the following problem. So you draw two samples. Either they are from joint independent distribution or from joint distribution. So they consider what is this problem to distinguish these two hypotheses. It looks like a similar problem, but let me show you why it is not. Okay. So first of all, let me draw these time samples from a renewal process. So that means that all these variables are statistically independent. I draw it from some distribution. And I'm going to form a perfect forwarding. Every packet will forward immediately. So I get two measurements. They're both renewals, but these two are exactly the same. Okay, so clearly this is hypothesis 1. Someone is forwarding packets. Right? So now let me just throw one packet here randomly. And then you would find out that this will be, it used to be, because of this initial timing change, now the two measurements will be completely independent. Because this will correspond to that, and that is independent of this. This will correspond to that, and that is independent of this. Right? So this will become an IID. All you need is one sample that sort of disrupts the timing. Okay, so the timing is crucial in this formulation. Okay. So now I'm going to tell you how I'm going to do the detection. In fact, it seems to be impossible to do because I really haven't imposed any condition except the causality and delay. So let's say you observe two measurements. These are two dose transmission activities. Clearly, it's possible these are just drawn from independent transmissions. And you say, okay, in fact, I can pick up a subset of points. Maybe they're transmitting. Maybe they're forwarding. Okay, this packet is transmitted to node 1, is forwarded over here. It's causal, it satisfies the delay constraint. I'll pick this two, looks like it's causal. I can pick a subset of transmission epochs in both nodes and say, okay, there's some packets forwarding going on. You have many, many choices. Not only this, maybe this one also qualifies that. So you keep looking for additional transmission epochs that may satisfy this. So this shows that there's something impossible to do because this is drawn from independent realization, and you can pick a subset of transmission epochs that in fact forwarding packets. Right? So two hypotheses have the same measurements, and you shouldn't be able to detect them. And indeed, that's the case. You can't detect them unless you become greedy. Right? You're going to try to match many, many transmission epochs to forward packets. So if you do that, then if you just draw independent realizations, you shouldn't be able to do at certain rate. Okay. You can hide sort of small amount of packet flow, but if you try to be greedy and exceed certain threshold, you're going to have to review it yourself. Okay. So this is the overall plan of our attack. So we're going to define, so I've given these realizations, I'm going to define if there is a flow that is embedded, I'm going to define something called a relative flow rate. In the denominator is total packets in the flow. In the numerator will be the total packets involved as a part of the flow. Okay, so if there's a flow carried through the traffic, this will be what I call the relative flow rate. It's between 0 and 1. Okay, so what does our result really involve? Having a threshold on this relative flow. Okay, what I call sharp threshold C, I mean the following. If you try to carry a flow at a rate below this C, there's no way to detect. You can hide it perfectly, but once you try to carry information beyond this threshold, then it's always detectable. Okay, so fundamentally, there's no way to detect every kind of flow unless this flow exceeds certain thresholds. So if you do money laundering, you should do a small amount, not too frequent. Okay, so another way to look at this is that this C is the maximum amount of information you can hide using independent transmissions. So everybody transmitting independently can hide a subset of these transmission epochs and use that to forward information. So that's the maximum amount of information you can hide. And we're going to look at, okay, so what are the strategies to define, to actually have an impact on C? For example, you can use Poisson processes to generate these points, or you can use other kind of processes to generate these points. Okay, so that's what our goal is. To characterize this threshold you know that if you go beyond this, it will be detected. Below that, you cannot detect. Okay. Okay, so this is just to say what I mean by detected reliably. This is the so-called kernel of consistency, which simply means that as you collect more and more samples, the probability of false alarm and probability of misdetection both go to 0. Okay, so that means reliable in the long run. Okay, so this is a little bit wordy here. So this theorem essentially says such sharp threshold exists. If you give links rate lambda I and the delay constraints, okay, regularity condition by me actually I can only solve the renewal case. Okay, there exists a threshold that below that there's no way to detect. Above that you can detect it perfectly. For the Poisson case in particular, okay, if everybody use Poisson transmission schedule, this rate, this threshold is characterized by lambda times delta divided by 1 plus lambda delta. This, in the Poisson case, I can characterize exactly. And this forms, in fact, the basis of my detector. I'm going to show you how I'm going to do detect. Before that, here, in order for me to get this formula, the Poisson assumption is explicitly used. But that can be removed. If I have a renew process, then there's a analytical expression exists, but you have to solve integral equations. Otherwise, you have to do some kind of Monte Carlo run to get this number. And this also shows that it is rather easy to hide information, or it's rather difficult to detect the flow if lambda times delta is large. So if you have the rate of these points up here is very busy, it is much difficult for you to see, okay, subsets of these things, you know, whether there's someone trying to hide the traffic or not. Similarly for the delay case. Okay, so here is, the argument, yeah.
So the lambda is arrival rate.
Say it again?
The lambda is arrival rate.
Yeah, it's just the link rate.
Okay, so we haven't considered a constraint on the link capacity. We assume the link capacity is infinite.
I don't know how to define link capacity. In this case, what's happening on a link is just your transmission activity. So I don't know how you define capacity in this case.
Oh, so what I mean is that the transmission is noiseless, so the transmission is perfect.
So as a eavesdropper, I don't even know what noise.
Okay.
I'm just recording your time.
Okay.
So there's no capacity involved
so
at all. It's
nothing,
just measurements.
I see.
I
I see.
don't really care what kind of bandwidth they use, and I'm just recording when it transmits. This is a packet level, I guess. It's not like a symbol level. Clear? Yeah. Okay. Okay. So what kind of argument I need to make something like this? So the only part, what I need to show is that if I transmit at a rate less than the capacity, there's no way to detect it. Okay. If I hide the information flow at a rate below the capacity or below the C, the threshold C, there's no way for me to detect it. So how do I do that? The way I do that, I'm going to construct a strategy to forward packets so that it will be just like independent transmission. So first I will draw two independent Poisson processes. I'll just draw points. Okay, so S1 and S2. So I'm going to select a subset of these points in S1, subset of these points in S2. They form a causal match and satisfy the delay bound. Okay, because I'm drawing this from independent Poisson processes, there's no way for you to distinguish whether it is truly independent or I'm using it to transmit information. Right? The difficult part is to show that there's a maximum number of pairs you find that satisfy the causal and delay constraints should not exceed this number, C, that I'm giving you. Okay. So that's the part that involves most analytical things, but that's the basic line of attack. But this is not a detector, right? This is like if you transmit this, there's no way to detect. The other side of the story is, of course, if you transmit at a rate greater than this, you must reveal yourself. For that, I need to construct a detector that does just that, right? In fact, I'm going to do the same thing. So first, you give me the measurements, S1, S2. I'm going to have to find a real good algorithm that find the maximum number of matches, causal matches, that satisfy the delay bound. Okay, so if I have an algorithm that find the maximum number of matches that satisfy delay bound, then I can look at this relative flow ratio for the one I found. Okay, because I'm finding the best one, this R hat must be greater than R. Since you're transmitting greater than the threshold, I can test of my relative flow against the threshold. I already know. Okay, so I don't know how you forward packets, but I have a procedure to find all eligible, the maximum number of eligible transmission epochs that you can use, you could have used for forwarding information. Because I'm doing the best, therefore this has to cross the threshold. Okay. So again, here there are two difficulties. One is, how do you know what's the best way to find this matching that is causal and satisfy the delay constraints? Second is, you look at these time averages, right? In the numerator is how many epochs you used for the transmission. Denominator is total number of transmission epochs. How do you know this will converge to something that is going to be greater than C? Okay, so that's really the difficulty of this problem. So now let me describe first this. I think that's what I'm going to do next. Yeah, this is not my invention. This is actually probably even done earlier than this. So my students like to use this analogy. You can think of this way. So you have two conveyor belts. Okay, they go this way. One conveyor belt has boxes that line up, arriving like a poisson. The other one are money, okay? Stack of money also arrive as a poisson, okay? And you want to find these two arrivals within a delta time, and you want to box them. You want to find the maximum number of matches so that you can put the money in the box and then take home, okay? Intuitively, it seems to be a rather complicated thing because there's all kinds of possible matches you have to consider. And it turns out that it's an extremely simple procedure. It goes like this. Okay, so you look at the first one. Okay, here is money. Okay, and you look at the second one. Is there a box available within delay delta? If there's one, you box it. Okay, so this you put in this box. This you put in this box. This box you can't find money. You throw them away. So this is not part of the information flow. Okay, okay, this you can box. This one, the money arrives, but you have no box, right? So you throw them away. Too bad. Okay. So here, clearly, you have partitioned the transmission epochs into two sets. One that satisfies the delay bound. The other one are things that cannot match. Extremely simple procedure, completely linear. The amazing thing is the optimal you can do. It's really surprisingly. Okay. So this is the best maximum number of matches you can ever find. So the algorithm of detection is rather simple. You give me S1, S2. I run this algorithm. I will find out those that qualified as information flow. I will compute the relative flow rates. How many I find over here divided by the total. And I compare that with the threshold. If it's go beyond that, I declare that someone is forwarding information. If it's below that, I'll say either it's independent or the flow rate is too low that I cannot detect. Procedure clear. This is an extremely simple algorithm. So what about the multiple flow? Okay, so you have not just one pair, you have multiple of them. The algorithm simply generalizes. You keep doing this to find the box that is within delta. Once you find it, you go to the next step. There is a bag. You can bag the boxes, and you keep doing this. Once this matching doesn't exist, you count them as noise. It's no longer qualified. This is still optimal. It's still the maximum number you can find. You just have to do a hypothesis testing again. And what is interesting and also intuitive is that as you have more and more these nodes monitored, it gets more and more difficult to hide information. So the amount of information that you can hide that is not detectable decays exponentially. Okay. So the point is there's no way to hide long hop information while hiding a single hop is relatively easy to do. And it's exponential decay. Okay. So if you want to hide transactions, you don't want to hide like you go to, I don't know, Jamaica Bank, and that's a bad idea. You should go one hop. And the next thing is, what about a traffic distribution? Okay. Clearly, how these things arrive should affect how many pairs you can use for transmission, hiding information. Okay. Now, and we also know that for internet traffic, it tends to be more heavy-tailed traffic rather than Poisson, right? So what this show is that for heavy-tailed distribution, it's much more difficult to hide information. You can think about it as bursty, and if you have delay constraints, if you want to use some transmission to transmit information, a lot of those points are not eligible. Right? This shows that this is sort of a threshold. Lower the threshold, the less information you can hide. So for heavy-tailed distribution, it's a lot more difficult to hide information. It's a lot easier to detect, and comparing with light-tailed distribution. Okay, so this is like the Pareto distribution. I want to say the same thing. When do I have? 1:30?
50, yeah.
1:50?
No. 50 minutes.
Okay, I'm almost.
We started a bit.
Yeah. Okay. So now, all this up to now, sort of I'm reporting the real numbers, sequence of real numbers to the fusion center. That's sort of unacceptable for people who are working on distributed detection. You have to quantize them. So I'm going to talk about what are the quantization scheme. Here, this part I have clean results, okay, sharp threshold. Here I have ad hoc results. I don't have as clean result, but I have ways to solve the problem. I can consider two different ways of quantizer. These are probably what you would have think about when you have this problem. I'm going to have a time axis partitioned into periodic time intervals, hours or days, and I'm only going to report how many packets I see. This is one level of quantization. So today, I saw 5 packets on this link. Tomorrow, I didn't see anything. Okay, like some kind of guard sitting on a door and recording how many people pass through, right, out the door. So you record something like this. You don't really record specific timing. You just record how many. 1-bit quantizer would be even simpler. I just say, okay, someone passed here, no one passed here. Okay, so every node you monitor, you will give this sequence of 1 and 0s, or for this case, you give sequence of integers, right? Clearly here you need only 1-bit information, at most, right? Here you may need more, but since we are given rate constraints, okay, so you can show that at least for Poisson, this thing grows, all possibility the entropy grows sublinearly. So that means if you choose this t long enough, you should be able to satisfy the rate constraint. Doesn't mean that is the best thing you do, best thing you can do, but clearly no problem of satisfy the rate constraint. All I need is, given this quantized version, can I still use the same technique to detect the flow? Okay. The answer is yes, but you have to do a lot of modifications. So this is what I just described for real number. Okay, this is the case. This is one of the channels is quantized. The other sensor is not. It's like you give me your information. I have my real measurements. You just tell me you see 3 people today, 5 tomorrow. So I can use mine to pair with yours. Okay, so this is actually called quantization with side information. Okay, which is a one step toward both quantized value. This essentially what you do is you use the same algorithm, you line up all the points at the beginning, you do the match. Okay. Simple generalization. And if both of them are quantized, you have both of them lined up, you do the match. Okay. So we have algorithm to do that, but it's a little bit complicated to describe. What about if 1 bit? 1 bit is the complication even more. So you have to do like a forward matching and a backward matching, but the concept is still the same. You try to match potential legitimate transmission epochs that may have happened. Both of them you can show that they insert the minimum numbers, then you have the threshold, you compare with threshold, you declare. Okay. So one should characterize somehow the rate allowed for transmission versus how sensitive is your detector. So I'm going to try to make something like a rate and sensitivity function. I will say that a detection is more sensitive if it can handle more noise. Smaller percentage of information rate, more percentage of chaff packets. Okay. So if it can detect flows with smaller rates or larger number of noise, and will measure the sensitivity against a rate allowed. So these are actually this is a single 2-hop flow, 2 nodes involved. These are 3 nodes involved, 4, 5. This actually shows as you increase the number of hops, your detector will be more and more sensitive. Okay. These are on Poisson processes, and nobody in computer science people would believe something like this, right? They won't trust you to generate. So you have to do with traces. So this is the student who did the traces on the internet traces. So I guess people post these kind of traces on the web. You just grab them, you run. The basic question, our intuition is this: Poisson is the most difficult traffic to detect. Internet traffic is a bit more bursty and makes it harder to hide information. So we just want to use, what we want to do is use Poisson to figure out this threshold and see how effective it is. Okay. So this is the sensitivity for actual internet measured traffic. This is the Poisson case. And this, in fact, validate that experimentally. This is something like choose 2 out of 40. There we have like 40, we have total 40 pair of, 40 traces, and you randomly pick 2. Okay, so you can compute this. Anyway, so it's sort of, at least in part, makes us feel a little bit more comfortable about using Poisson as a way to find the threshold. Let me just conclude. So this is the kind of the setup we have. Each individual sensors just measure the timing, and they will send information to the fusion center through some kind of rate constraint channel. And you want to design this quantization scheme as well as detector so that they can detect whether there is someone forwarding information. Okay, so if there's no quantization, if it's real numbers, we have fairly sharp result that says when it's possible, when it's not. With that, we don't know. We have some achievable results. Okay, so now we are looking at not just one-way traffic, but 2 ways. You want to sort of figure out, are these 2 people talking to each other? They're doing IM or something. Because what's relied upon in our detector has to be a sequence of packets, cannot be one packet. If you just want to transmit one packet, hide secretly, you have to have information more than just timing. But if you just keep doing it, you're playing a game, ultimately you will reveal yourself. Okay, so we are looking at 2-way communication, whether you can detect the 2 users are communicating with each other just by looking at the timing. Looking at the multicast case, are there a set of nodes that involve receiving some kind of streaming? And ultimately, what I want to do, but I don't know how, for the lack of model, is whether there is a chat room that you can detect certain nodes are participating in some kind of chatting events. right? So those require some kind of different model, different constraints. I just don't know how to attack that problem. The simple thing we have used here is delay bound. You sort of require that, you have to delay it within certain bound. That's all I want to say.
Any questions?
Here in the algorithm you described, it seems that the delay constraint is extremely important here. So can you explain again how do you determine the delay constraint in your simulation? Or
Well, I consider that's given. So I'm not design a delay constraint. I assume I'm gonna assume that if the flow is propagated through the network, everyone would not delay more than delta. I have to be given that number.
That's a given number.
That's a given number. I don't know how to design myself. So even if it's not strict delay, the average delay, I think average delay you can probably measure end to end what kind of average delay.
That's kind of measurement.
Yeah, measurement is possible, but straight delay is a lot harder to do, right? But the average delay problem, we don't have a sharp result. We have results of how to do it, but we don't have a sharp one. So that means this particular way of matching is no longer valid. It's no longer optimal. You can still do this, use the average number, but it's no longer optimal. That means the flow you are able to detect, are much more significant flows than the minimum amount. So the average part is actually a lot more challenging. But it's definitely more practical, right? You just measure the end to end. You say, okay, so this kind of flow, I don't know, like video streaming, what kind of delay you can tolerate, right? I guess that you can sort of have a measurement. Right now, I'm just assuming I'm given.
Also, the quantization part, who is doing that? The node or the fusion center?
No, the node.
Okay.
Of course, the node you want to transmit very little, right?
Yeah.
So each one just say quantize either 1 bit or, I observe activity, I observe no activity.
Thank you.
Yeah.
You talk about the effect of traffic pattern on segmentability because your analysis is based on the Causal. So you mentioned that, for example, for like heavy-tailed traffic, it may be more easier to be detected.
Yes.
So can we understand that, for example, like the periodic pattern is the most difficult to detect?
It's periodic. In fact, if everybody transmitted exactly periodically, you're probably hopeless.
Yeah.
You can imagine, right?
But I just think if it's periodic pattern, then it's like very dependent because it's like the period is same. So do you mean that? So in your comparison, the average for those different distribution of traffic pattern is the same, right?
Yeah, rate is the same.
So it's possible that there is the variance effect. So basically, because you said the more burst traffic seems to be easier to
detect. Yeah.
So do you have like some result, for example, like the effect of the variance of the traffic pattern on?
I don't think variance by itself would characterize this. I don't think one thing is remarkable about this algorithm is that it's optimal on the realization basis, which means that it's independent of what kind of traffic you have, it's always the best. So it's an extremely strong algorithm. The only thing that relates to distribution is the threshold. Because to calculate threshold, you need to show convergence, and the convergence to what value depends on the distribution of this renewal process. So that part, what we are trying to do is to compare a class of distributions. In fact, if you read it, it's a Weibull distribution that you can characterize with a tail value, right? So in that class, we show that the heavy tail is definitely easier to detect. So I don't want to make it more than it sounds, but I guess intuitively it is reasonable to expect. If you have a bursty traffic, it's much difficult to hide because of the delay bound.
Okay, so I'm just wondering whether there is some relationship between the variance of the traffic and the delta, because you are comparing under the same delta.
Delta means delay, or
The delay bound. So
yeah. Right now we are not looking. I don't know. I don't know whether you can say that. Whether bigger variance, I guess intuitively might be true. Bigger variance you may have. I think it has a lot to do how they distribute rather than just variance itself. You can imagine there are sort of extreme cases, a lot of the small variance, and you have very big variance. But I think that's a very sharp question. I don't know what it is. Within certain class I can say. But I don't think the variance itself is enough to say. I don't know. Good.
Any other questions? Well, if not, let's thank our speaker.
Thank you.